We have started titration in the last class. So, let's suppose, basically, I was telling you that titration is the neutralization reaction in which acid is going to react with an alkali in the presence of any indicator, and they are going to form salt and you can say water. But the purpose of titration is to find out the concentration of unknown substance by using the known concentration. This is the purpose of you can say titration. We can find out the concentration of an unknown substance by using the known substance. Okay, let's suppose I have this HCl. Okay, and I know the concentration of this HCl, that is 0.1 mole per decimeter cube. Okay, and I want to find out the concentration of this sodium hydroxide, this is X. So I can find out this concentration by using titration, because we have the relation that is C1V1 is equal to C2V2. By using this relation, we can find out the concentration of an unknown substance by using the known substance. This is the purpose of the titration. But if you ask what is the reaction, so I would say that this is a neutralization reaction. Okay, and then I told you in the last class that let's suppose we have a conical flask. Let's suppose we have a conical flask. Okay, let me tell you again. Wait. Let's suppose this is the apparatus of the titration. Okay, and I took this conical flask and added some drops of indicator. Okay, and then this is the indicator that I have just added into this conical flask, and then I have taken a burette in which I had sodium hydroxide. Okay, in the burette I have NaOH. In this I have hydrogen chloride, hydrochloric acid. Okay, hydrochloric acid, right? Okay, so hydrochloric acid plus few drops of indicator. I think I told you that we were adding phenolphthalein in this conical flask. Basically, phenolphthalein is an indicator, okay, which changes its color. Phenolphthalein is an indicator which changes its color in the presence of alkali. You know, phenolphthalein is pink in the presence of alkali, but it's colorless in the presence of acid. Remember that acid, if you are going to add indicator in an acid, okay, so this would be colorless. Okay, I'm talking about you can say phenolphthalein indicator. I'm talking about phenolphthalein indicator. Okay, and if you are going to add indicator in an alkali, so it would be pink. Okay, and then we have discussed that let's suppose I have taken 10 cm cube of acid into this conical flask with a few drops of indicator, and then I'm going to add sodium hydroxide from the burette. Obviously, when you are going to add sodium hydroxide from the burette to the conical flask, obviously they are going to have a neutralization reaction. Obviously they are going to have a neutralization reaction. Okay, they are going to have neutralization reaction. So let's suppose I have added 8 cm cube of sodium hydroxide into the conical flask. So how much acid is left? You will say, sir, 2 cm cube of acid is left. Then I would say, will you see any color of indicator? You will say, sir, no. Then I ask, why you are not going to see any color change? Because you will say that, sir, in the presence of base, that phenolphthalein is pink in the presence of base. Okay, so in the conical flask right now, there is no any base. There is no any base because still the acid is left. That is 2 cm cube. Okay, and then in total I have added 10 cm cube of alkali through the burette. Then I would ask how much acid is left behind. You will say, sir, there is no acid. Then I would ask, will you see any color change? You will say, sir, no. Then I ask why? You will say there is no acid and there is no alkali into this conical flask. All the contents are neutralized. Then you will add a few more drops of sodium hydroxide from the burette to the conical flask. Then suddenly you will see the color change from colorless to pink. Okay, suddenly you will see the color change. It indicates that just stop the titration. Why? Because all of the acid that you have taken in the conical flask has been finished. So you are supposed to just stop the titration. Okay, so now you are going to add extra amount of sodium hydroxide into the conical flask. That's why the color is going to change from colorless to pink. This pink color represents that in this conical flask we have extra base that is not being neutralized. Okay, because the titration has been completed so far. So this pink color indicates that the titration is completed, the neutralization reaction has been completed. Okay, so this is the purpose of the titration. So when you will see the pink color into this conical flask, this is called end point, this is called end point, this is called end point. So end point is not an accurate point. Remember, end point is not an accurate point. Okay, end point is not an accurate point, remember. Okay, so because when you see the pink color, obviously when you see the pink color, it means that there is an extra amount of base. Okay, there is an extra amount of base. Okay, when you see the pink color, it's mean that there is an extra amount of base, remember, right? So I can say that endpoint moles of acid is not equal to moles of base. This is not an accurate point, right? And then also, I want to have exact point. I need to know what is the volume at which there is 100% neutralization. I don't want to have more amount of sodium hydroxide. Okay, I don't want to have more amount of sodium hydroxide. So what am I supposed to do? I'm supposed to use I'm supposed to use pH titration. I'm supposed to have pH titration. Okay, what is the benefit of the pH titration? What is the benefit of the pH titration? In this titration, we are not going to use any indicator. Okay, so we would be having just pH meter. Okay, just a pH meter, right? So if you can see this, this is a pH meter which is dipped in this conical flask, in this beaker. Okay, pH meter is dipped into this beaker. You can see the pH meter. This is a pH meter, right? This is a pH meter which is dipped into this you can say acidic solution. Obviously you will see the pH that is equal to 2 or 1 or 2 or 3, because this is a strong acid. A strong acid is going to have a pH that is equal to 1 comma 2 comma 3. Okay, so when you are going to add more base in it, when you are going to add more base in it from the burette, obviously the pH is going to increase. Obviously the pH is going to increase because you are going to add more amount of base into this beaker to neutralize this acid. So the pH would be increasing. So it would be going through just 3.5, then 4, then 4.5, then 5, then 5.5, then 6, then 6.5, and then 7. So when the pH becomes 7, it means that the solution has completely neutralized. Okay. Now you are supposed to just stop the titration because pH is equal to 7. It's mean that there is a salt and water into this conical flask, or you can say a beaker. So pH titration is quite more accurate as compared to those titration in which you are going to have an indicator. Okay. Because indicator will show you the color in the presence of extra amount of acid or extra amount of base, right? Because there is no any indicator which shows its color like exactly, like you can say accurately, when there is no acid and there is no base into the conical flask. There is no any type of, there is no any such indicator. So that's why we go for the pH titration. pH titration is quite more accurate. Okay. So after doing this pH titration, when you will see the pH that is equal to 7, so obviously it's mean that it is completely neutralized. Now you are supposed to stop the titration. So that's all about the titration. That's all about the titration. Okay. So then after doing that, uh, now if you are thinking that, sir, is that necessary? Sir, is that necessary when the pH is equal to 7? So now, like we are supposed to just think that the titration has been finished. Is that mandatory? So the answer is no. So the answer is no. If I ask why, so just look at this. Just look at this. Just look at this. I am going to react this sodium hydroxide with hydrochloric acid. I need your attention. I'm going to react sodium hydroxide with this hydrochloric acid. You know that sodium hydroxide is very strong base, very strong alkali, and also hydrochloric acid is a very strong acid. Okay. They would react together to form sodium chloride and water. Okay. So I mean strong alkali, strong alkali is going to react with a strong acid. It produces neutral salt. Neutral salt. So remember, there are multiple salts. We may have neutral salt, we may have acidic salt, we may have alkaline salt. When you are going to prepare any neutral salt, when you want to prepare any neutral salt, so you are supposed to react a strong acid with a strong alkali. When you are going to react a strong acid with a strong alkali, so it's going to produce a neutral salt. Then you can say that, then you can say that, then you can say that the pH is equal to 7 for these titrations. For this reaction, the pH is equal to 7. So neutralization is going to take place when the pH is equal to 7, because this is the neutral salt. This is the neutral salt. Okay. But this is not mandatory that always you will see pH is equal to 7 at neutralization point. No. What if you are going to react any strong base with a weak acid? With a weak acid. Can anyone tell me what type of salt I am going to obtain? Acidic salt, basic salt, or neutral salt? Yes?
Basic salt.
Basic salt, exactly. Basic is the, you can say, is the dominant property. This is a stronger one. This is a dominant one. This is a dominant one. Okay. So basic salt and water, basic salt and water, remember. Okay. So and what if And what if you are going to have, a strong acid with a weak base?
Acidic salt.
Acidic salt and water. Okay, let's suppose I want to make ammonia. Let's suppose I want to make ammonium chloride. Let's suppose I want to make ammonium chloride. Can anyone tell me, is this neutral salt, basic salt, or acidic salt? Yes, can anyone tell me? Yes, acidic salt. How? How can you say that this is an acidic salt? Yes. How can you say that this is an acidic salt? Yes, Kashaf, can you tell me this is an acidic salt? So let me tell you, ammonia, when it's going to react with HCl, as you know that this is weak base, this is weak alkali, and this is an acid. So they are going to form this salt, that is acidic salt, because this is a strong acid. So strong property would be dominant. Okay. So then, are you getting my point? And what if I want to make this? Can you tell me what type of salt is this? Yes. Yes.
It is a
Mm-hmm.
basic salt.
So basically, it can be made by this ethanoic acid and this sodium hydroxide. Obviously, this is weak acid. So strong property would be dominant. So that's why this is a basic salt. This is an alkaline salt. So that's why I'm saying that for those salts which are acidic salts, so their neutralization point would be in the range of acid. Okay, would be in the range of you can say acid. And then those salts which are the basic salts, okay, uh, so their neutralization point would be in the range of basic pH, like greater than 7, like greater than 7, right? Greater than 7. So we would see pH curves. We would see the pH curves in which we would be looking like how the salt is going to be formed and what is the neutralization point. So all of this stuff we would see when we would be doing, when we would be drawing the titration curves. So before drawing the titration curves, let me tell you something. Tell you something. There is a term that is called equivalence. There is a term that is called equivalence point. Equivalence point. This is the point when mole of acid is equal to the mole of alkali. This is very accurate point. This is very accurate point, okay, as compared to the end point. If you are going to have a comparison, so this is very accurate point. Equivalence point, when the moles of acid are equal to the moles of base, okay, this is very accurate point. So let's suppose, okay, uh, HCl versus NaOH. HCl versus NaOH. Okay, I have just taken HCl in the conical flask. I need your attention again. This is one-time investment. You will be understanding each and every titration after looking at this. In this conical flask, I have HCl, and obviously I have dipped a pH meter in this flask as well. This is a pH meter, pH probe. Okay, and then this is the burette. This is the burette. In this burette, we have an NaOH. What do you think? What do you think? What do you think that when you are going to add a pH probe, pH meter into this conical flask, what the pH you will see? Can you tell me an idea? What pH you will see into when you are going to dip any pH meter into this conical flask? Yes? Mm-hmm. Yes. No
There
idea?
was
No idea.
any
Basically,
number,
you will
sorry.
see the pH 1, 2, or 3 if you're going to have a strong acid. Obviously, HCl is a strong acid. Obviously, HCl is a strong acid, right? HCl is a strong acid. So you will see the pH that is equal to, that may be 1, that may be 2, that may be 3. It depends on the strength of acid. And then when you are going to add sodium hydroxide from the burette, obviously the pH would be increasing slightly. Obviously the pH would be increasing slightly, so the time would come then when the pH would be equal to 7. Okay, like the neutralization is going to take place during this titration, obviously. So what we are supposed to do, okay, and if you can see this is volume of NaOH added, and this is the pH. Obviously I have dipped a pH meter into this conical flask. Okay, I have dipped a pH meter into this conical flask, and in this conical flask we have an acid. So obviously I would see the pH that is equal to 1. Let's suppose I'm considering any strong acid. So this is 1. So it starts from 1. It starts from 1. I'm going to add more amount of base, then this is neutralization, and this is the line becomes straight. So when the line becomes straight, when the pH is equal to 14, let's suppose, okay, then the pH is equal to 14. So this was the initial pH, and this is the final pH. If you are going to draw these type of lines, these type of you can say titration curves, so remember you need two things. The first one is the initial pH from where you are supposed to start your curve, and the final pH, like from where you are going to stop your titration curve. So these are two very important things that need to be, you can say, you must consider these terms before going to draw any type of titration curves. So initial pH and the final pH, okay, and then this is very important to know this volume. You must know this volume at which the neutralization is going to take place, basically. Then see the straight line. see the straight line. The half of the straight line is the neutralization point. Okay, this is neutralization point, or you can say equivalence point. Equivalence point. A straight line divided by 2. A straight line divided by 2. I am considering that the straight line is of 5 centimeter. If you are going to divide this 5 by 2, so that would give you the equivalence point. It would give you equivalence point. So this graph is of strong acid versus strong alkali. This graph is on, you can say, strong acid with strong alkali. We have 4 types of titration. We have 4 types of titration. Okay, you can say a strong acid versus a strong base, a strong acid versus weak base, weak acid versus a strong base, weak acid versus weak base. So this is one of the titration in which I have done like the strong acid with a strong alkali. So I would see these type of curves if you are going to have a strong acid and a strong alkalis. Okay, so can you can you draw this strong acid and weak alkali? Can you draw this, please? Can anyone just draw and then send it to the group? Yes, have you done? Just look at this graph. Look at this curve. With the help of this curve, you're supposed to draw. You're supposed to draw. You can say strong acid versus weak alkali. Strong acid versus weak alkali. Right? Okay. Fast, fast, fast. Fast. Hasib. This is Hasib. This is Hasib. Okay. This is Hasib. Strong acid and strong alkali. And weak alkali. Oh, nice, Hasib. Nice. Good. Good, good, good. One more. I'm waiting for Shamim, Kashaf, and Tal, and also Faisal. Just do this. Let me tell you this curve. See this. See the curve. See the curve. This is for strong acid and weak base, weak alkali. It's starting from 1. It shows that this is a strong acid and it's ending at 8 or 9, which shows that this is a weak alkali, which shows that this is a weak alkali, which shows that this is a weak alkali. Okay. 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 Done.